Hello everyone, welcome to another session on maths for data sciences. So in a previous session we looked at what is an expected value of a random variable. It is nothing but a mean or an average value of a random variable. And then we looked at something called variance, which is the measure of spread of the random variable. And for both the mean and the variance, we looked at how we can compute it. So the mean was computed as the sum product of the values of the random variable with their corresponding probabilities. And once we have computed the mean, we can calculate the variance as the difference between the second movement of x, which is expected value of x square, minus the square of mean, which we calculated above. So now going forward, we'll be looking at deriving the mean and variances for the various discrete distributions which we looked at. So starting with the uniform distribution. So let us say we have a uniform distribution with the values 2, 5 and 9. And since there are three values here, and we know that for uniform distribution, the probabilities of each of these three values should be equal. Therefore, the probabilities for each one of them should be equal to 1 by 3 each, since the sum of the total probabilities is always 1. So, the mean is very easy to compute here. It is 1 by 3 times 2 plus 5 plus 9, which is nothing but 16 upon 3. So this is very intuitive, given that we could have simply calculated the arithmetic average of the three values, which is 2 plus 5 plus 9 by 3 again, and it would have given us the same answer. This is because in a uniform distribution, all these three values are equally likely. Therefore, a simple arithmetic average would be equal to the mean of the random variable. Now moving ahead, we want to calculate the variance, which is computed as expected value of x square minus 16 by 3 whole square, because this is mu square. Now expected value of x square is computed as 2 square multiplied by the probability plus 5 square multiplied by the probability plus 9 square multiplied by the probability minus 16 upon 3 whole square. So now this can be calculated as 4 plus 25 plus 81 whole divided by 3 minus 256 upon 9. This is calculated as 81 plus 29, 110, and then we multiply it by 3 to get the denominator as 9 minus 256 upon 9, and this is 260, so 40, 30, 70, 74 upon 9. So this is the required variance of the uniform distribution, which had three possible values, 2, 5 and 9, and all of them are equally likely since it was a uniform distribution. So this is how we compute the mean and variance of a uniform distribution. Now going ahead, we would be deriving the same for a binomial distribution. Now let us say we have a binomial distribution with parameters n and p, and we already know the probability mass function from our previous sessions for binomial distribution is given as nc x p raised to power x 1 minus p raised to power n minus x. So if you remember, this represents the number of ways to select x of the n trials where we'll have the event that will happen. P to the power x is the probability of x events to happen in the n trials, and 1 minus p raised to power n minus x is the probability of event not happening in n minus x total trials. Now the expected value or the mean of the random variable is calculated as summation of x px. This can be written as summation of x ncx p raised to power x 1 minus p raised to power n minus x. Now this could be written as summation of x. So we just open this combination operator using the formula. It is n factorial divided by x factorial n minus x factorial p to the power x 1 minus p n minus x. This could be written as, so we basically take one n out here and one x out here. So we get summation of nx upon x, and we are left with n minus 1 factorial divided by x minus 1 factorial and n minus x factorial. We also take one p out from this particular term, so we put it here, and we can write this as x minus 1, 1 minus p, n minus x. Now this could be, so we just cancel out the x and x here. N and p are constant, so we can bring the parameters which are constant outside the summation operator, and we are left with summation of n minus 1 factorial divided by x minus 1 factorial, n minus x factorial, p to the power x minus 1, 1 minus p raised to power n minus x. This could be written as n minus p summation of n minus 1 c x minus 1. So if you notice, the term which we obtained here, the term which is filled with factorials, it is given as the combination operator n minus 1 c x minus 1. So we get the same combination operator here, and we keep the rest of it the same. So p raised to power x minus 1 into 1 minus p raised to power n minus x. Now if one notices here, this is nothing but PMF of a binomial distribution with n minus 1 and probability p. And since we know, so we can write this as np summation of p. Let us call this particular random variable, the binomial random variable with parameters n minus 1 and p as y. So we can write it as py equal to x minus 1. This is because we are finding the probability for x minus 1 here, as you can see from here, as well as you can see from, so one can see from here and from here. We are actually finding the probability for y equal to x minus 1. Now this term is nothing but sum of all probabilities for a random variable. Now if you remember from our very first session, we know that sum of all probabilities of a random variable across all its values should be equal to 1, and therefore we get the required value of mean here as n times p. So mean of a binomial distribution with parameters n and p is given as the product of the parameters n and p itself. So this is how we compute the mean of the binomial distribution n into p. Now moving on to variance. So for variance, we need to calculate the second movement of x as well minus mu square. Now mu we already know, this is equal to np as we have derived here. So we just need to calculate the second movement of x here. Now once again, using the same process, we use a summation and then ncx, which is n factorial divided by x factorial multiplied by n minus x factorial, p to the power x 1 minus p raised to power n minus x. Now what we do is we cancel, so we basically bring out, so since we have x square here, we can bring out n into n minus 1, so x square n into n minus 1, and from denominator we bring out x into x minus 1. So we write this together, and we are left with n minus 2 factorial divided by x minus 2 factorial and n minus x factorial, and px 1 minus p raised to power n minus x. Now we cancel one of the x here, so we'll be left with x upon x minus 1 multiplied by n into n minus 1, and then this could be written as n minus 2 c x minus 2 p raised to power x 1 minus p raised to power n minus x. Now writing this particular term as x minus 1 plus 1, so we just added and subtracted 1 from numerator, and we keep rest of the terms the same. So we are left with, we can write this x minus 1 plus 1 divided by x minus 1. So this particular term here could be written as, I'll just write it here. This could be actually written as 1 plus 1 upon x minus 1. So for 1, we just are left with the remaining of the terms here, n into n minus 1, n minus 2 c x minus 2, p raised to power x, 1 minus p raised to power n minus x. And for the second term, plus 1 upon x minus 1 plus summation 1 upon x minus 1, n into n minus 1, n minus 2 c x minus 2, p raised to power x, 1 minus p raised to power n minus x. Now this could be written as, so we just bring n into n minus 1 and p square out in the first summation, and we are left with summation of n minus 2 c x minus 2, p raised to power x minus 2, 1 minus p raised to power n minus x. And for the second summation, we only bring out np, and we are left with summation of, so this x minus 1 and n minus 1 are again multiplied with this particular combination operator to get n minus 1 c x minus 1, and p x raised to power minus 1, since we brought only p out in this case, 1 minus p n minus x. Now if one note here, both the summations are nothing but probability distribution function or probability mass function of a binomial distribution, and since we are summing up the probabilities, both these summations have to be equal to 1. Thus we are finally left with n into n minus 1 p square plus n into p. Now to calculate the variance, we will use the second movement of x from this expression, and we'll bring it here, and we'll have sigma square equal to n into n minus 1 p square plus np, and then minus mean square, which was np whole square. This could be written as n square p square minus np square plus np minus n square p square. Now we cancel out n square p square, and we are left with np minus np square. This is nothing but np into 1 minus p. So this is how we calculate the variance of a binomial distribution with parameters n and p. So just looking at the final formulas again, what we got here for binomial distribution with parameters n and p, the mean or the expected value is computed as the product of the parameters, while the variance is computed as product of parameters multiplied by the complement of the probability. So this is nothing but, this is sometimes also represented as q, and therefore we can write sigma square as npq, where q is the complement of probability, which is 1 minus the probability parameter itself. So this is how we compute the expected value and variance of a binomial distribution. So moving forward, we'll be looking at, so this will be an easy one, a Bernoulli distribution with parameter. So we have Bernoulli with parameter theta. This is nothing but the probability parameter, which we saw in the binomial distribution as well. So now let's say we have a Bernoulli distribution is nothing but, this is same as a binomial distribution with n equal to 1 and p equal to theta. Now for binomial distribution, we already know Ex is equal to np, therefore in this case it will be theta. And for variance x, we know it is np 1 minus p, therefore it will be theta 1 minus theta, since n is equal to 1 for a Bernoulli distribution. Another way to compute the mean and variance would be to look at the probability mass function of a Bernoulli distribution. So we already know there are only two possible values for a Bernoulli distribution, that is x equal to 0, which is 1 minus theta, and x equal to 1, which is theta. So this is the probability of the event to occur, and in that case x will be equal to 1. Now to calculate the expected value, we are calculating the mean as the sum product of x with their corresponding probabilities. This is 0 into 1 minus theta plus 1 into theta, which is theta. And this is the same value which we got from the binomial distribution. Now for variance, we need to calculate the second movement of the random variable, and it is computed as summation of x square px, which is nothing but 0 into 0 square 1 minus theta plus 1 square theta, and this is equal to theta. Therefore sigma square, which is second movement, minus mu square is calculated as theta minus theta square, which is theta into 1 minus theta, which is again the same formula which we got using the binomial distribution earlier. So this is how we calculate the mean and variance of a Bernoulli distribution. Moving forward, we'll be looking at geometric distribution. So geometric distribution was a distribution which was used to model a random variable which counts the number of trials required to get the first success. And we assumed here that the probability of success in each of the trials was equal to p, which is a parameter of the geometric distribution. Now, one don't have to really remember this different probability mass functions because they are very intuitive from the definition of the random variable itself. Since geometric distribution is the random variable which represents the number of trials required to get the first success, we'll have x minus 1 failures and then 1 success. So the probability of x minus 1 failures is nothing but 1 minus p raised to power x minus 1, and then we'll have 1 success. Now once again we'll calculate the mean of the random variable as summation of x px, which is, so let us say we start with, so x could take values 1, 2, 3 and so on till infinity. So for x equal to 1, the probability is p, since the first trial has to be success. For x equal to 2, the probability is 1 minus p into p. For x equal to 3, it's 1 minus p square into p, because we need 2 failures and 1 success for total 3 trials, and this goes till infinity. Now let's call this mu. Now multiplying both sides by 1 minus p, so both LHS and RHS by 1 minus p, we are left with 1 minus p into p. So this particular term when multiplied by 1 minus p gives you this particular term, and then this particular term will give us 2 into 1 minus p whole square into p, and so on. Now if we subtract the second equation from the first one, we'll be getting, we can take mu common, 1 minus p is equal to p. So this particular first term, this term comes directly, and then we subtract 2 into 1 minus p into p with 1 minus p into p, so we'll be left with 1 minus p into p, and then we are left with 1 minus p whole square into p, and this goes till infinity. So this is mu p equal to the same term. We cancel out the p and we are left with mu equal to 1 plus 1 minus p plus 1 minus p whole square till infinity. Now this has become a geometric progression, infinite geometric progression, with a equal to 1 as first term and r equal to 1 minus p as common ratio. Now a sum of an infinite GP is calculated as a upon 1 minus r. So since a is equal to 1 here, putting the values, we get 1 upon 1 minus r, which is 1 minus p, and therefore we get the value of mean here as 1 upon p. So this is how we compute the mean of a geometric distribution, and it is computed as the reciprocal of the parameter of the distribution itself. Now moving on, for variance, we again need to calculate the second moment of x and subtract the square of mean from the second moment of x. Now to calculate the second moment, we have 1 into, so 1 square into p plus 2 square into p into 1 minus p plus 3 square into p into 1 minus p whole square, and so on till infinity. Now once again we multiply both the sides with the 1 minus p, and we'll be left with p into 1 minus p plus 2 square p into 1 minus p whole square, and so on. Now once again we subtract, so we subtract here, and 1 minus p is nothing but p into e x square. Once again we bring the p as it is, plus 2 square minus 1 square is 3p 1 minus p, 3 square minus 2 square is 5p into 1 minus p whole square, and the next term, let's write another term, that will be 4 square minus 3 square, so 16 minus 9, that will be 7p into 1 minus p whole square till infinity. Now once again cancelling out p, we get 1 plus 3 into 1 minus p plus 5 into 1 minus p whole square plus 7 into 1 minus p whole cube till infinity. Now multiplying both sides with 1 minus p, we have 1 minus p plus 3 into 1 minus p whole square plus 5 into 1 minus p whole cube, and so on. Now once again subtracting the terms, the second equation with the first one, so this particular equation will be left with p into ex square equal to 1 plus 2 into 1 minus p plus 2 into 1 minus p whole square plus 2 into 1 minus p whole cube, and so on. Now clearly the right hand side has become an geometric progression, so this could be written as p into ex square is equal to 1 plus 2 1 minus p plus 1 minus p whole square plus till infinity. Now this is a GP, infinite GP, with a as the first term 1 minus p and r is equal to 1 minus p as well. So we can write the sum once again using the same formula for sum of an infinite GP. We have a upon 1 minus r, which is a upon 1 minus r. So we are left with 1 plus 2 1 minus p, this is p, and if we divide both the sides by p, we are left with 1 upon p plus 2 upon p square minus 2 upon p. So this is 2 upon p square minus 1 upon p. Now putting all the values together to get the variance, we have sigma square 2 upon p square minus 1 upon p. So this is ex square, and then minus 1 upon p whole square, because this is nothing but mu square here, and therefore we are left with variance as, so 2 upon p square minus 1 upon p square will be 1 upon p square minus 1 upon p. This is 1 minus p upon p square. So this is how we compute the variance of a geometric distribution. So we have the variance, and the expected value for a geometric distribution was 1 upon p. Now one of the familiar thing which we have seen earlier, if you remember, what is the expected number of trials required to get the first head in a fair coin toss. If you remember, we saw this earlier, and what we did was we were calculating the values of probabilities for each possible outcome, and we saw if the first is h, then x is 1 and the probability is 0.5. If it's th, this is 2, this is 0.5 square, this is tth, this is 3, this is 0.5 cube, and so on. This problem can be actually modeled as a geometric distribution with p equal to 0.5. And now, since we already know the expected value of x, which is mu, is calculated as 1 upon p, therefore we get the answer directly here too, for which we had to earlier calculate the expected value using the summation of x px. So if you remember, we had done that and we had still got the same answer. So in this case, we can directly use the expected value of geometric distribution as 1 by p to get the required mean value. So this is one of the application of geometric distribution, where we are calculating, or we are putting the random variable x as the number of trials required to get the first head. So the first head itself is defined as a success here, or as an event here, and each of the coin toss is actually a trial here. So this is it from this particular session. For the last discrete distribution, Poisson distribution, we need to first look at another concept called Taylor series to actually derive the mean and the variance for the Poisson distribution, and therefore we look at it in another session.